All right, everybody. I think we're ready to start. Thank you for coming to NDC Oslo. This is the first talk of the day. There's going to be functional programming talks in this room all day long, and tomorrow as well, and Friday as well. So if you're interested in functional programming, just stay in this room all day long. And there's also a functional lab, which I think is going to be in room 10, kind of going outside and then going up, where we're going to, at lunchtime. So if you have any questions about functional programming, you can come and talk to people like me and Thomas and Matthias and so on. Right, let's start. So this talk is the power of composition. It's a talk for beginners in functional programming. So if you're already familiar with functional programming, this is probably not very interesting to you. I have a website, F# for Fun and Profit, so I'm very into F#. And we have a F# consulting business if you're interested in that. So for beginners in FP, I'm going to be using F#, which is a functional language, but the concepts will work in most programming languages, except maybe COBOL or something. So it's really about the principles behind functional programming and composition in particular. People go on about composition a lot in functional programming, and I just thought I'd have a talk which tells you what they mean. So I'm going to start off by talking about the philosophy of composition, and then I'll talk about functional programming principles, because this is a beginner's talk. So functions and how to compose them, types and how to compose them, and then we'll actually get into some meat and we'll actually look at composition in practice. We'll start with two really simple examples, and then we'll do FizzBuzz. We'll do a kind of really complicated version of FizzBuzz, just for fun. And then we'll talk about the whole monad things. And then I'll demonstrate how you can actually build a web service using composition. So no objects anywhere. No objects were harmed in this talk. So let's start with philosophy. Okay, so in order to understand composition, you have to have been a child at some point. And the reason is because you have to have played with Lego. And hopefully everyone here has played with Lego. And hopefully everyone here has also played with toy trains. So this is going to be very important, and you'll see why in a minute. And in fact, you actually don't have to have been a child at some point, because it turns out there's a lot of adults who really like playing with Lego too. So if you Google AFOL, Adult Friends of Lego, there's a whole world of adult Lego people there. So what is the Lego philosophy? So, Lego philosophy. All pieces are designed to be connected to each other. And if you connect any two pieces, you get another kind of piece that can be connected to other kinds of pieces. And the pieces are reusable in many different contexts. So let's go into that a bit more. Here's some Lego. And you can see every single piece has little bumps on it, right? They're all designed, every piece is designed to be connected, right? There's no pieces which you can't connect. And if you connect two pieces together, you get another kind of piece. So you start off with one thing and you put a piece on it, and that gives you another kind of bigger piece that you can glue things on top of. And then you can take that bigger piece and glue things on top of that, and so on until you've made something. And what's cool is you don't need a special kind of adapter to glue things, to connect things. You can just, they're designed to be connected inherently. You can just literally touch things together, put things together, and they work. And you can keep adding and adding until you make a really big thing, like this. Okay, so this is a giant piece of Lego. And it's not finished. You can add things to this too if you had enough pieces, right? So this thing of adding and adding and making bigger things out of small things, that is the whole principle of composition. Now, there's something else important, which is that the pieces are reusable. They don't just make one kind of thing. You can build a plane out of them, and then you can take the same pieces apart and reuse them in a different context. Okay? They're designed to be reusable. They're not designed, you can't just make a plane and then never use them for anything else. Okay? They're designed to be generic reusable pieces. And that means they have no strings attached, because if they had little strings attached, you wouldn't be able to take them apart and reuse them, because the strings would get tangled together, literally, right? So I mean, if each Lego piece had a power cable, you'd end up with some sort of horrible mess like this. So the very fact that Lego pieces don't have power cables, they don't have strings, they don't depend on anything outside the piece. The pieces are completely self-contained, right? That's a really important principle. Because if they weren't self-contained, they wouldn't be reusable, they wouldn't be composable. So there's the power of composition. with Lego. Now, we can do the same thing with wooden railway tracks. So I'm sure you've all played with Brio or something like this. Again, all the pieces are designed to be connected. You can connect pieces together, and they're reusable. So here's some wooden railway track. And they're designed to be connected because every single piece has a little bump in it, just like Lego, right? And you can literally glue them together. You get a bigger piece of track. Okay, you don't need special adapters. You can just literally do that, right? No special adapters needed. And because of that, you can keep adding and adding and adding until you make a really big thing. So there's a big thing made some smaller things. And there's the power of composition. This whole thing of gluing things, starting with small things, gluing them together to make bigger things. I'm going to go on and on and on. The power of composition, I'm going to say that over and over because that's the title of this talk. The power of composition compels me to say the power of composition. All right. Again, they're reusable. You can make one little layout, and then you can take it apart and make another layout. Okay? This is obvious. I mean, if you couldn't do this, these toys wouldn't be fun, right? The whole reason why these toys are fun to play with, why Lego is great and why wooden railways are great, is because they're fun. You can, like, do something and take it apart and do something else. All right, let's move on to programming. So the UNIX philosophy is actually very, very similar. And I stole this from the Wikipedia article, so don't blame me, if I don't get this right. So, write programs that do one thing well. That's one of the philosophies. And if you need to do something new, start a new piece. You don't complicate old programs by adding new features. Each piece is a little small thing that does one thing well. And then you write programs to work together, which means that you design your programs to expect input from programs you don't even know about. You expect them to be working in a bigger system, so you design them to work with input and output. And then finally, you make them use text streams, because that's the universal interface. Well, that's maybe not the best universal interface, but it's a pretty good interface. It certainly was pretty good for the 1970s when Unix was designed. So this maps very well to our composition philosophy. The pieces are reusable, the pieces are designed to be connected, and they don't need any adapters. You don't need a special kind of adapter when you're piping things between Unix components. Right, no special adapters needed. So the Unix philosophy is a philosophy all about composition, which is why, again, it's very, very popular. Okay, so that's enough philosophy. Let's talk about functional programming. So functional programming. Like I say, this is a bit thing, so I'm just going to go through some very basic stuff about functional programming. A couple of core principles. So the first core principle of functional programming is it's all about functions. Functions are things. And I'm going to use the analogy of a little bit of railway track, like this. The second important principle of functional programming is that you use composition everywhere. So you don't have objects, you don't have variables, you don't have all this stuff. You just have functions and you glue them together. Composition. Just like Lego. And the final thing is, if you're coming from an OO background, the types in a statically typed functional programming language like F# or Haskell or Scala or something, types are not the same thing as classes. Okay, they're sort of more like sets, and I'll demonstrate what I mean by that in a minute. So let's start with functions. So a function, like I say, I like to think of it as a little bit of railway track. And it transforms inputs to outputs. There's a little tunnel on this railway track, and it's the tunnel of transformation. So something comes in one side, like an apple, and it comes out the other side, and it gets turned into a banana. Okay? So this is a very simple function that turns apples into bananas. And in functional programming, we tend to write this apple, arrow, banana. That's how we'd indicate what the function does. So very important that functions are standalone things. They're not attached to a class. They're not methods. They're standalone things. And why that's really important is that, by the way, and standalone is just another word for reusable. Right, standalone means you can reuse it. So there's no strings attached. So because it's a standalone thing, it can be used as inputs and outputs of other functions. And let's look at some examples of that. So here's a function with an input, and here is the output being another function. Or here is a standalone function, and it's got a regular output, but the input is another function. Like that, okay? Or here is a standalone function, and it's got a regular input and output, but there's a parameter, which is a function, and that parameter can be used to control how the function works, for example. So having functions as inputs and functions as outputs and functions as parameters, that's a very simple principle, but you can actually build really complicated systems from that way of doing things. For example, you can have a function that returns a function that generates other functions that pass to parameters. You know, you can really build complex things, but the fundamental principle is pretty straightforward. And we'll see an example of a function that returns a function shortly. So that's the first principle. Functions are just things. So we haven't talked about classes, we haven't talked about objects. All we've got is functions. Now the second thing is, you've got all these functions. How do you build things from the functions? Well, the answer is composition. So here's how function composition works. You have two functions, one that takes an apple to a banana, one that takes a banana to a cherry, say, and you want to glue them together to make a bigger function. Well, I think it's pretty obvious how you glue them together. You literally take the output of one and you stick it into the input of the other, right? So you take these two things and you kind of smush them together, and now you have a new function. All right, that's before, that's after. Yeah, hopefully that's kind of common sense. It's really obvious how you would do this. It's just like the model railway track. What's interesting about this new function, though, is that you can't tell that it was built from small functions. There's no seams. In particular, where did the banana go? Right? The other functions had bananas. This function doesn't have any bananas anywhere. So you've got data hiding. You've got abstraction already. So when I'm giving you this function, you don't know about bananas. All you care is about apples and cherries. And you can repeat. You can take this thing and glue it to another function that uses cherries and hide the cherries. So the fact that the level of the function doesn't matter. You don't know whether this is a high-level function or a small-level function. They're all exactly the same. Functions are just functions. So a very important point, though, is in order for function composition to work, they have to be self-contained functions with no strings attached, just like the Lego, right? If they've got strings attached, you can't glue them together because they get tangled up. So what does strings attached mean in terms of programming? Well, it means the data has to be immutable, because if you change the data inside a function, you're messing with stuff. The function might not work. The order of the functions that you use makes a difference, for example. There's no side effects. That's another way of saying it. It's not changing anything in the outside world. There's no input or output. You're not writing to the file system. You're not writing to a database. You're not messing around with global variables. So that does restrict the kinds of things you can do with pure functions. There are ways around this, which we'll talk about. But basically, if you have these kinds of pure functions, you can compose them really nicely. Right, this no strings attached rule is really important. In fact, Joe Armstrong, who created Erlang, has a whole famous quote about this. He said, "I think the lack of reusability comes in object-oriented languages, not in functional languages." Why is that? The problem with object-oriented languages is they've got all this implicit environment that they carry around with them. You wanted a banana, but what you got was the gorilla holding the banana, and you got the entire jungle. So this is the thing. If you've ever tried to refactor a complex object, you can't just pull the method out, because the method depends on a local variable, and the local variable depends on something that was dependency injected, and the thing that was dependency injected depends on something else. Sometimes it's really hard to refactor because there's all this implicit things going on in objects, and in functions there's no implicit. Everything is explicitly passed in and explicitly comes out. There's no kind of mysterious side effects. There's no strings attached. All right, so that's composition. Let's look at a real example. Let's say we have an add one function and a double function. Okay, and in F# we'd write it like this: add 1 equals x plus 1, double equals x plus x. Very simple. And we just use this little double angle bracket. That's the composition thing. So I just take these two functions and I smush them together, and I get a new function, add 1, and then double it. So in pictures, we've taken these two things, we've smushed them together. We have a new function, and we can just call it like it was any other function. We just say if we pass 5 to it, we get 12, for example. So we can't tell that this function was built from smaller functions. And if we have 3 functions, we can smush them all together, add 1, then double it, then square it. We're literally smushing them together with a composition, And then we've got a new function, we can just call it. If we call it with 5, we get 144. So that's composition in practice. It's pretty simple. Now, there's another way of doing composition, which is actually much more common in F#, and it's called piping. And the reason why piping exists is because calling functions with parameters can often get really messy. So let's say we call add1 with 5, okay? But then we want to double it, and then we want to square it. We end up with this kind of nested parentheses, and it's very hard sometimes when it's really nested to find out where exactly to start from. You have to start from the middle and kind of work your way out. So that can be kind of confusing. So an alternative way of doing this is that you kind of start with one thing. Use the piping model, just like UNIX piping. You start with one thing, you take 5, and you pass it into add1, and that gives you 6. And then you take the output of add1, and you pass it to double, and that gives 12. And you then take the output of double, and you pass it into square, and that makes 144. So you're just taking this number, and you're taking it into one function, taking the output, passing it to the next one, taking the output, passing it to the next one. Exactly like UNIX pipes. And this is actually a lot easier to understand, and you'll see this all the time in functional programming. And so in F# we have this pipe symbol, which is a vertical bar with an angle bracket. The vertical bar is, on its own, is used for something else. So it's almost like the UNIX pipe symbol, but not exactly the same. Okay, so we're going to be using pipes. Every time you see that in the rest of this talk, that's what it is. It's the pipe symbol. Pipes everywhere. All right, so now that we've got composition of 2 functions, let's see how we can build an entire application from functions. Okay, it's composition all the way up. So let's say we have a couple of low-level operations, like uppercasing a string. So uppercasing a string is a pure function. You pass in a string, and you get another string back. So that's pretty obvious. It's a function. Now, if you take these low-level operations and you glue them together, you might get a kind of a bigger set of things called maybe a service, okay, like an address validation service, for example. And you pass in an address, and you get back some validation result. And for people under 30, I just have to explain what a service is. It's just like a microservice, but without service in front. Yeah, service is a very old-fashioned word. Right, so we got these services, we glue them together, and we glue them together into a sort of scenario or a use case or whatever you want to call it. Let's say update your customer data or whatever. You pass in a request, you get back a result. And by the way, this is not request response, this is input output. This is a subtly different approach than OO. So you're not sending a message and getting a message back. You have an input and output, the railway track model. Okay, you take all these use cases and you build them into a web application. So a web application has some sort of HTTP input, has some sort of output, and inside the web application you basically have a controller or a dispatcher or whatever you want to call it that decides which one of these things to run based on the request that comes in. And we'll actually see an example of how to do this at the end of this talk. And notice there's no objects. Right? You say, well, how can I do this without objects? There aren't any objects. You'll see in the final example that there's no objects anywhere. It's all just functions. So, what's interesting about this thing about composition is it's a kind of fractal, self-similar kind of thing. You use exactly the same techniques to compose big things as you use to compose small things. It's just like the Lego again. Gluing 2 Lego pieces together and gluing 2 massive Lego things together. It's exactly the same kind of principle. And if you had a kind of a complex web app, this is what it would look like. There'd be all these little functions inside, and they'd be routed or routed through the functions based on the request and the response. So this is what a functional app looks like. And that is the power of composition. I have to say it again. Right, so power of composition with Railway, power of composition with Lego, and all the other kinds of power composition we're going to talk about. Now, functional programs love composition so much that they have all this jargon around it. And there's a lot of jargon that you'll hear, which is really, if you think about it, just ways of making composition easier. it will make a lot more sense. So, for example, you'll hear the word monoids. And that is really just a way of combining things like strings and lists and functions even. You combine two things to make another one of the same kind. That's typically called a monoid. Monads, another big buzzword in functional programming. And monads is all about how can you compose things which have effects, not necessarily side effects, but that have more than one output. And we'll actually see an example with the FizzBuzz later on. And finally, category theory. Functional programmers love to talk about category theory. And one of the reasons is because you can sort of think of category theory as composition theories. It's like, what happens if I take this thing and I connect it to this thing? Is that the same thing as if I connect this thing to this thing? You know, it's about composition. It's not really about composition, but I hope no mathematicians are actually listening to this. I apologize to the mathematicians, but it's good enough for you. Right. Okay, the final principle for functional programming is that types are not classes. Okay, they're more like sets. So if a type isn't a class, what is it? So if you think of our function, it has an input and output. And a type is just a name for a set of things. So here's all the set of valid inputs for this function. And here's the set of valid outputs for this function. So we just give these set of valid inputs and set of valid outputs, we just give it a name. So for example, if this function can take any possible integer, or these set of numbers, we call that set type integer, or int32 or whatever. If it can return any sequence of characters, we say that's type string. If it can take any kind of person, we say that's of type person. But it's not the same thing as a class. It's just literally a list of all the people in the world, conceptually. A list of all the people in the world, give that set a name, person. Okay, there's no behavior. It's just a set. And here's an example of a set of fruits. And because it's just a set, of course, you can have a set of functions. So this is a set of functions which turn fruit into fruit. So this is the fruit-to-fruit functions. And we give that set a name. We call it fruit-to-fruit functions, So because it's just a set, it's nothing special. Now, because they're just sets, types can be composed. And we call this an algebraic type system, or I'd rather call it a composable type system, because you can glue types together to make bigger types. And that is only possible because types don't have behavior. Right? Behavior is done separately from the types. And because it's just sets of things, you can do set union, you can do set intersection, you can do all kinds of things. You can do sets and make bigger sets. So in an algebraic type system, you build new types from smaller types. Two possible ways. One is you AND them together, and the other is you OR them together. So what do I mean by that? So when you AND things together, you might say, well, to make a fruit salad, I need an apple and a banana and a cherry. So those are the three things I need, and I need all of them. And this is typically called, a record or a tuple. So in F# we'd write it like this. We say a fruit salad is an apple and a banana and a cherry. And this is, so you can see it's kind of got fields sort of like JavaScript. And the type of apple is an apple variety, so that it itself is a type of all the possible apples in the world. So that's a record type in F# with curly braces. Now, the other kind of way of composing types together is something you don't get in C# and Java, which is ORing them together. So if I want a snack, I could say, well, I want an apple or a banana or a cherry. Just one, not all of them at the same time, just pick one of those three. So this is the kind of thing you can't really do. It's sort of like an enum in C# and Java, not exactly the same. And in F# we'd write like this. A snack is either an apple or a banana or a cherry. And of course, with each thing, there's a type that goes along. If it's an apple, it's the set of all possible apples it could be. If it's a banana, it's the set of all bananas it could be. So I call that a choice type. In F# it's called a discriminated union. You'll sometimes hear them called sum types and so on. So that's very, very important type, and we'll see why it's really useful in a minute. So here's a real-world example. Let's say that you have some sort of payment processing system, and you accept three kinds of payment, like cash, checks, and credit cards, say. Now, for cash, there's no extra information associated with it. For checks, we need a check number, and for credit cards, we need a credit card type and a card number, right? So how would you implement this in your language of choice? Well, if you were using an OO language like C# or Java, you'd probably kind of start with an interface, like a payment method interface. It would have some methods on it or something, and then you'd say, well, cache is a kind of subclass, or it inherits or implements that interface, and then you'd have another subclass for check, and you'd have another subclass for credit cards, and so on. So they'd all implement a particular interface or inherit from a particular abstract base class. So that's kind of OO way of doing it. It's all about the behavior. Each interface has a certain behavior. Now in F# we probably wouldn't do it this way. We would compose types like this. So we'd start off with some primitive types, like a check number is just an int, a card number is just a string, and so on and so forth. We take these basic concepts and we build bigger ones from the smaller ones. So we'd say a card type is a choice. This is a choice type between a Visa and a MasterCard. And a credit card information is a record. It's an AND. So we say it's a card type and a card number. Okay, so it's a record. So there's a choice type to make a bigger thing and a record type to make a bigger thing. Okay, now we've got these things. Now we build stuff on top of that. We say, well, a payment method is a choice. It's a choice between cash and check. And if it's check, we need the information from the check number that we defined above. And if it's a credit card, we need the information from the credit card that we defined above. So we're building on top of the types we defined earlier. And that's a choice type. And then we can build on top of that, and we can say, well, okay, a payment amount is a decimal, that's a primitive. Currency is a choice between euros and dollars, say. Okay, another choice type, another primitive type. And then we can build an even bigger type. Say, well, payment is an amount, it's a record, it's an amount, and it's a currency, and it has a method. So it's a payment, and each one of those, in turn, the amount is a payment amount, or the payment amount was defined earlier. The payment method was defined as the choice type. So we're building a bigger and bigger set of types from a very small initial set of primitives. And you can keep going and going. You can now make the payment part of an order or an invoice or something, and you can then make the order. But anyway, you can see you can just keep building and building bigger and bigger types from this basic process. Okay, so record types, which are AND types, and choice types, which are OR types. So bigger types from smaller types. That's the power of composition. Okay, you've heard it before. Now, what's cool about doing this with the types is you get kind of executable documentation, which is something we kind of always go for, to have the documentation as part of the code. So if I showed you this code, a suit is a club or a diamond or a spade or a heart, and a rank is a 2 or a 3 or 4 or so on. A card is a suit and a rank. A hand is a list of cards, a deck is a list of cards, a player is a name and a hand. And a game is a deck and a list of players. So this is all executable code, but it's, I think you can guess what I'm talking about here without having to look in 20 different files, look at the 200-page requirements document or something. This is very nice. So we've got using types here to represent nouns, but we can also put function types in there. So we can say to deal, you start with a deck, that's the input, and you output a new pair. You output a new deck, because the deck's immutable. So when you've taken a card off the deck, you have a different deck with one less card, and now you also have a card on the table. So the output is a card on the table and a smaller deck. Or to pick up a card off the table, you start off with your hand, and there's a card on the table, that's the input, and after you've picked up your card, you now have a bigger hand, and there's no card on the table. So you can actually represent verbs with types as well. So this is pretty cool. We've actually represented the entire domain on one screen. So it's not scattered around in 20 different files like you might have in C# or Java. It's literally on one screen, which is very useful if you're trying to do domain-driven design and you want a domain expert to kind of go through this with you. Because if a domain expert looks at this, they could actually, even though they're not a programmer, they could look at this and say, actually, you missed out, a kind of suit. Maybe you need Joker in there or something and you forgot about it. So here's a more real-world example. If I showed someone this code and I say, what payment methods do we take? Can you guess what payment methods we take? It's pretty obvious. You just look down this list. Yeah, we take 3. You don't have to look in the documentation. You don't have to dig down to the code. This is really obvious. So typically in a functional program, you'd have something like this as the sort of first file in your program, and it would define the domain for the rest of the system. And so this is code, but it's also documentation. And if you change this, the rest of the code won't compile, and you'll have to fix it up. So this is a massive topic. If you're interested in DDD and designing with types, I have a whole talk on that on my website. And I also have a whole book about this, if you're interested, Domain Modeling Made Functional, which is available in the bookstore right here. And if you want to get a signed copy, come and grab me. Right, OK, so that's enough theory. Let's talk about some real code. So we'll start with a very, very simple example, which is think of a number. So this is the children's game. Think of a number where you say, think of a number, add 1, square it, subtract 1, divide by the number you first thought of, subtract the number you first thought of, and the answer is 2. Isn't that amazing? Absolutely incredible. I don't know how this works. So anyway, so this is, let's implement this, okay? So we're going to use this composition idea. We're going to have each little piece is going to be a little bit of railway track, and we're going to glue the railway track together. So we're going to start with a number you thought of. We're going to feed it into the first one, which adds 1, and we're going to take the output of that and feed it into subtract 1, take the output of that, feed it into square it, and so on and so forth until we get the final answer. Okay, so this is the design we're going to use. So let's actually look at the code. So we're going to define little helper functions for each step. So to add 1, we just add 1. To square it, we square it. To subtract 1, we subtract 1. To divide by the number you've thought of, we do that. So we're going to define all these little helper functions. These are the little bits of railway track. And then, once we've got the helper functions, we can just do the piping thing. We start with a number, we feed it into add 1, we take the output of add 1 and feed it into square it. We take the output of square it, feed it into subtract, so we take the output of that, and so on and so on. And that gives us the final answer, which is 2. So this is a complete little program written using nothing but functions, okay? It's object-free code. All right? Okay, well, this is a very kind of trivial example, so we'll look at some more complex code. But it gives you an idea of how you might write something using nothing but functions and composition. So I hope this makes sense. All right? Okay, it's not always that easy. Of course, this is a very trivial example. So what we've got here is we've just got 2 functions, each with 1 input and 1 output, and we glue them together, and we get a new function, and everything is good, and everything is very easy, and there's no problems. But, of course, the real world is never that easy, so let's look at a couple of challenges. The first thing is, what happens if you have a function with 2 outputs, right, instead of 1 output? Right? Some functions are more complicated than that. Some functions have 2 inputs, right? They're not always 1 input, 1 output. So if you have a function with 1 output and 2 inputs, how can you glue them together? All right? It seems like it'd be impossible to do that. So that's our first challenge. What happens if it's got 2 outputs and 1 input? How do you glue those together? That seems pretty hard as well. So that will be our second challenge, and we'll look at both of these challenges in the rest of the talk. So let's start with the first one, composing multiple inputs with Roman numerals. So 2 Roman numerals, to make something into Roman numerals, this is our little task. We take an integer like 5, and we turn it into Roman numerals, which we use a v. And so, 12 would be x11 or whatever like that, okay? So hopefully everyone's familiar with how this works. So here's the design we're going to use. We're going to base the design on the fact that Roman numerals are based on a tally system. You make 4 marks, and when you get to the 5th mark, you put a line through it, all right? And hopefully, maybe that's where the v came from, I'm not sure. But it's a tally system. So what we're going to do is, if you want to convert, say, 17 into Roman numerals, we're going to make 17 copies of the I, letter I, okay? 17 I's. And then every time you see 5 I's in a row, we'll replace it with a V. And every time we see 2 V's in a row, we'll replace it with an X. And every time we see 5 X's in a row, we'll replace it with an L. And every time we see 2 L's, we'll replace it with a C, and so on. So this is a very, very simple implementation. Nothing complicated about it. And I wouldn't say it's highly performant, but it's probably good enough for what we need. But it's a really simple model for the design. Okay, and we keep going and going and going, depending on how high you want to get. So again, we have these little bits of railway. The way we're going to do it is the little bit of railway track. We're going to start by replicating it however many times, and then we're going to replace 5 I's with a V, and replace 2 V's with an X, and replace 5 X's with an L, and so on and so forth. All right, so that's the design. Here's the problem, is the replace function that we use has three inputs. You have the original input string, and you have the old value and the new value, and that gives you your new output. So replace is a three-input function, all right? And that's a problem, because we can't compose, something with one output with something with three inputs. All right, so this is not good. So all the composition patterns we talk about really only work for functions which have one parameter. If you have more than one parameter, they don't work. So that's like bad news, right? Well, the good news is that every function can be turned into a one-parameter function. It's one of the key things about functional programming. You can always do this. And this is a technique called currying, named after Haskell Curry. And currying sounds really complicated, but what it really is just taking a two-parameter function and turning it into a one-parameter function that returns another one-parameter function. So after currying, we have a function which has one input, not two, and instead of spitting out the answer, it spits out another function. This is this whole thing of functions as inputs and outputs. So the output of this thing is another function with one input. So now we have a series of one-input functions. The first function takes one input, spits out a new function. The second function also takes one input and spits out the final result. So by having a two-parameter function, we've now turned it into a series of every single thing is now a one-parameter function. It's a really important point in getting your head around functional programming. It sounds more complicated than it is. It's actually pretty straightforward. But there you go. So let's actually look at that in practice. So because of currying, every function can be turned into a one-argument function, which means we can use these composition techniques. So here's replace, which is three parameters. So here's the original version. We have three parameters, and we return it. And so three inputs in there, three inputs in the code. All right, so that's how you might write it in something like C#. And we just return the string. But instead what we're going to do is do this. We're going to have a two-input function, and it's going to return a lambda. Okay, so it's got two inputs, and the lambda is going to be returned. And the lambda sort of has the old value and the new value sort of baked into it, right? So the lambda is a one-parameter function. So there's two inputs for the thing, right? There's only two inputs in the actual code, and the lambda itself is now a one-parameter function. So by doing this, we can get a one-parameter function which we can then compose together. Okay? So once you have these curried functions, you can sort of do the opposite and do something called partial application. Very important technique in functional programming. So kind of think of it, it's not the same thing as currying at all, it's sort of the opposite. So we have this two-parameter function, and what we're going to do is pass in those two parameters, but not the last parameter. All right? So the replace function has three inputs originally. We're going to pass in two of them and bake them in. And the final input we're not going to pass in. All right? So for example, if we want to replace five i's with a v, we're going to say replace five i's with a v, but the actual final third parameter we're not going to pass in right now. We're going to pass that in later on when we actually know what it is. We don't know what the actual input string is, but we know the two of the parameters, but we don't know the third one. So we'll pass in two of them for now, and we'll leave the third one for later. So that's a function. So when we call this, we're getting a function now, which is all it's missing is one extra parameter. Similarly, if we say replace two v's with an x, we can pass in the two v's and we can pass in the x. The final parameter, which is the string we want to replace, we don't know what that is, but now we have a function that we can actually use later on. Okay, so only two parameters are being passed in right now. So if we go back to our design, each of our steps is now a one-parameter function, and the things we're going to replace with are sort of now baked in to our steps. Okay, each little bit of railway track has the replace parameter sort of baked into it. So now we do have a series of one-parameter functions, and we can compose them. So here we go. We're going to define our helper functions, right? And then once we've got our helper functions, we can say replicate it however many times, do the replace, do the replace, do the replace, do the replace, and so on. And again, with our helper functions, we're passing in two out of the three parameters, and the third parameter is going to be passed in as part of this piping process. All right? Now, one thing is rather than defining all these helper functions, it's much more common just to define them in line. So, for example, if I want to add 2 to something, add is a two-parameter function. But I can say just add one, pass in one parameter and then have the second parameter passed in through piping. So for example, when I say add 2, it's missing a parameter. That extra parameter is going to be passed in through the pipe, which is 5 in this case. So this is going to be 5 plus 2. And then we're going to pass that into multiply. Now multiply, again, is a 2-parameter function. We're going to give it one of the parameters, which is the 2, and the second parameter is going to be coming from the pipe. So that goes the same as 5 add 2 is 10, or 5 add 2 is 7, times 2 is 14, or whatever. Okay, so if we look at our code, we don't have to have all those helper functions. We literally just inline the replace like this. So this is our final example, how we would implement it. What's cool about writing code like this is that you might have noticed that we actually don't have a very complete implementation, because in modern Roman numerals, if you don't have 4 i's in a row, you replace it with 1 v, and you don't have v11111, you have 1x. So we can easily add new segments. We can just say, okay, every time you see v111, just replace it with 1x. Every time you see 4 1s, just replace it with 1v, and so on. So this is our final implementation. This pipeline approach is really nice. Like I say, you can slot things in and out of the pipeline. You can add things, you can move things, you can add new features at the end, just like the UNIX philosophy. Okay, so that's this challenge of how do you deal with 2 inputs. That was our challenge, and I think we have dealt with that successfully using partial application. So this is why partial application is really important as a way of helping with composition. All right, another one, FizzBuzz. Okay, so FizzBuzz, for people who aren't familiar with it, print the numbers from 1 to 100, but if it's a multiple of 3, print fizz. If it's a multiple of 5, print buzz. And if it's both, print FizzBuzz, multiple of 15. Okay, so here's a basic implementation. If the number is divisible by 15, print FizzBuzz. If it's divisible by 3, print fizz. If it's divisible by 5, print buzz, and so on and so forth. Otherwise, you print the original number. And we have this little helper function called isDivisibleBy, which just says if it's divisible by, that's good. Well, this is a perfectly good implementation, but it's not good enough for us today because I want to do it in a different way completely. I want to make it a lot more complicated. And the way I'm going to make it more complicated is I'm going to use a functional approach using a pipeline. So what we're going to do is we're going to have all these little bits of track, and each one does one case. So we're going to handle the 15 case, we're going to handle the 3 case, we're going to handle the 5 case, and anything that we didn't handle will be the final remaining case. So how do we implement each of these cases? Well, we're going to handle a case. There's 2 possible choices for the output. Either it's what we call uncarbonated, which means nothing happened, right? Like you passed in 2 and nothing happened. Or it's carbonated, where you get back a string. You get back a fizz or a buzz, right? So how can we represent two different choices for the output? Right, 2 different choices for the output. How are we going to represent that? Well, we're going to represent it with a little bit of railway track. But this time, we're going to have 2 outputs in the railway track. Okay? So there's going to be an input, and there's going to be 2 possible outputs. One is the uncarbonated case, and the other is the carbonated case. So we're going to create a new type to represent these choices. It's going to have 2 choices. It's going to be a choice type with 2 cases. The first case is uncarbonated, in which case we have the original integer, or it's carbonated and we have a string like fizz or buzz or something. Right? So it's an unprocessed case and a processed case. So that's our type. So we're modeling our domain with a choice type. And then we're going to have our actual handle each case. I'm going to call this function carbonate. Okay? And if it's divisible by the thing, it's going to be carbonated, and we're going to give it a label. And if it's not divisible by the thing, it's uncarbonated, and we just leave it alone. Okay? So there's the carbonated case, and there's the uncarbonated case. All right? So that's our complete design right there. That's everything we need. And if you think this is particularly complicated, it is. And this is actually, Ragnwald used this as an example of how not to do an interview question. So if they ask you to do FizzBuzz in an interview, don't give them this answer. But I think for a technical talk, it's kind of a fun way of showing how to do functional programming. Right. Notice this has 3 parameters. It has the number like 3, the label like fizz, and the actual number that you're going to try and work with. All right, 3-parameter function. Pay attention to that. All right, so let's actually see this in use. So let's say we take 12 and we pass it into carbonate 3 with fizz. Now carbonate 3 with fizz is we're only passing in 2. The extra parameter is going to come from the 12 that we pass into the pipeline. Okay? So if you pass 12 into that, it says, yes, that's divisible by 3. I'm going to give you a fizz. If we pass 10 into that, it's going to say, no, that's not divisible by 3. I'm going to give you an uncarbonated 10. But if I pass it into carbonate with 5, so yeah, it does work, and I'm going to give you a carbonated buzz. Okay? So there's our little code, little testing our code to make sure it works okay. All right? Now, we have a problem. How do we compose these things? These railway tracks, they don't fit, right? So what we want to do is, if it's uncarbonated, we didn't process it, we want to go on to the next one. If it was carbonated, we want to bypass, we want to go all the way to the end. Once we've got it carbonated, we want to go all the way to the end and not do anything else. All right? So here's the problem. How do we compose these things? Well, the answer is like this. If you've ever played with a toy train, you'll know that you can actually make 2 tracks like this. So I call this the 2-track model of programming, otherwise known as railway-oriented programming, and I have a whole talk on this if you're interested. And it's a nice idea in theory, but let's see what the problems are, because if you want to compose 1-track functions, it's really easy. You just take the output of one and feed it to the input of the next one. And if you have 2-track functions, they're easy to compose too, because you take the output of one thing and connect to that, and you take the output of the second one and connect to that. So that works fine too. No problem composing 2-track functions like this. But what we have is we have a function with 1 input and 2 outputs, and they don't compose. Right, so this is our problem. This is our challenge. So let's look at our first implementation. We're going to take the result from 15, and if it's carbonated, we're done. If it's uncarbonated, we have to go to the next step, which is try 3. If we get 3, if it's carbonated, we're done. If it's uncarbonated, we have to try 5. And if that's done, if it's carbonated, that works. If it's uncarbonated, then we get the final result. So this is an implementation, but it's really, really ugly. I mean, this is a horrible, ugly code. But there's a pattern. We can make this code a lot simpler if we notice there's a pattern. And the pattern is that every time we have an uncarbonated case, we do something. If it's uncarbonated, do something. If it's uncarbonated, do something. If it's uncarbonated, do something. That's the pattern. So let's take that pattern and run with it. So if it's carbonated, we're done. But if it's uncarbonated, we do something. Okay, that's the pattern we're going to try and turn into code. So we're going to parameterize. What is it we're going to do? Well, it depends. We don't know. So let's write the code. If it's I'm going to call this function if uncarbonated do. Okay. So if it's carbonated, we say it's done. If it's uncarbonated, we're going to do something with the number, but we don't know what it is. We're going to call a function with that number. Where does that function come from? It's going to come from a parameter. So this is parameterize all things. We don't know exactly what we want to do, so we're going to pass it as a parameter. It's a function parameter. Fine. So it's a function as a parameter. Now, with this if uncarbonated do function, our code is actually a lot simpler, because we start with carbonated by 15. If it's uncarbonated, we use the carbonate function with the next one. If it's still uncarbonated, we do the next one. And if it's still uncarbonated, we do the last step, which is slightly different because we have to do some special case with the carbonate. But otherwise, we can keep chaining these steps over and over and over again. So this code is a lot cleaner. It's a lot more linear. Now, obviously, this if uncarbonated do is a really weird way of doing FizzBuzz, but you'll see in a minute that it's quite important. Now, one more thing we said is that we've got FizzBuzz for one number, and we wanted it to work for numbers from 1 to 100. Now, in functional programming, you're not allowed to use loops. Well, you can use loops, but generally you don't. That won't work. You can't pass a list of numbers into a function with one number. So here we have a function with one number, and what we do is we use there's a special thing called a function transformer, which turns functions into other kinds of functions. And that, in this case, it's going to be list map. So list map turns a normal function into functions that work with lists. So after we've done list map, we now have a FizzBuzz that works with lists. And now we can pass in a list of things as input and get a list of things as output. So that's an interesting way of thinking about list map, or select in LINQ if you use C#. And you'd use it like this. You say FizzBuzz for lists is list map of FizzBuzz. So list map is a function transformer. So here's our final code. carbonated, if uncarbonated, do this. If uncarbonated, do this. Otherwise, do the last step. And to do it from 1 to 100, we say, here's 1 to 100. We feed that list of numbers into the mapped version of FizzBuzz, and then it gives us another list of things, and then finally we print those things out. So what's interesting about this is we're only doing the I/O, we're only printing things at the very end. Everything else is a pure function with no side effects. Unlike the first example I showed you where it printed right in the middle of the loop, this is a much more reusable kind of code. All right, and that brings us to the M word. So is there a general solution to handling functions like this? And the answer is yes, and the answer is bind. Bind is the answer. Bind all the things. FP people like the word bind a lot. So we have a very common problem in functional programming where you have these kinds of two things with two outputs, and they're not suitable for composition. If we could turn them into these kind of two-track things, they would be suitable for composition, because these things are very easy to work with. All right, so that's good. So we have a general problem of turning the top kind of thing into the bottom kind of thing. And that's what bind is. Bind is a kind of adapter block. If you think of the model railway again, you can kind of have a big block and you kind of slot the points function or the switch function into it, and you get a new two-track function. So there's a kind of a slot for a function, you pass in the points and you get back a two-track. So that's what bind is. So here's the implementation of bind for carbonated. So we pass in two things. Okay, if the input is uncarbonated, then we call this carbonation function. And if the input was already carbonated, then we just bypass. We never call the function. Okay, and this is exactly what our if uncarbonated do was. Right? This is exactly the same implementation as our if uncarbonated do, except this time we're calling it bind. So this brings us to monads. So monads sounds scary, but it's really not as scary as you might think. It's really a monad is just a data type and an associated bind function and a couple of other stuff which is really not important right now. So that's all it is. It's a data type and a bind function. So in our case, the data type was the carbonation result, which is that little thing with the two choices. And the bind function was the if uncarbonated do. So we just created our own monad in the last few minutes. And sometimes you'll hear the word monadic function, which is a switch or a points function, and then again you use bind to compose them. So there's the carbonate function like that. That was our monadic functions that we were working with. Okay, so that's all a monad is. It's unfortunately unfortunate terminology, but there you go, that's what we have. All right, so there's two outputs, one input, and that was our challenge number 2. How can we compose them? We compose them with monads. All right, one more example of using bind. So async tasks, async futures, promises, tasks, whatever you want to call them, you often want to connect them. When the task completes, do the next thing. Otherwise, you're done. Let's look at some code. So typically you might say start a task, and when it's finished, do the next thing, and when it's finished, do the next thing, and when it's finished, do the next thing, and so on and so forth. You get this thing called the pyramid of doom, which is pretty ugly. So let's see how monads can solve this problem. So we're going to have a bind function for tasks, and it says, when finished, do something, okay? And this thing that you do is a parameter. You don't really care what it is. It's just a function parameter that you're going to pass in, just like we did with the if uncarbonated. So once we've got this little bind helper function, we can rewrite that code as start the task, and then bind it to start another task, and then bind it to start another task. So now instead of having this kind of pyramidal going further and further out, you just have a nice linear line of things to do. So this is why functional people like monads for this kind of thing. One more example, error generating functions. So you often have a situation where you might have a website and you have some sort of input, you validate the request, you canonicalize the email, make it lowercase, for example, fetch a record from the database, update a record in the database, and so on. But the problem is there's all sorts of errors, like the name might be blank, you might not find the user in the database, you might get an authorization error. There's all these things that can go wrong. Right? So it's not a nice linear thing, you have to have all this error handling stuff. So to model this in functional way, we'd have all these different steps. So the validation step might or might not work. It's a kind of a two outputs. The lowercasing an email is always going to work. So that's a one input, one output. Fetching something from the database might or might not work. It might give an error, so that's two possible outputs. And updating something in the database might not return anything at all. It just does it and never returns. So these kinds of functions are not composable the way they stand. So one of the things that functional programmers do is spend a lot of time making these things into composable functions, and this is where the monads come in. So they're mismatched as they are right now, but if we use a map function, and we use a bind function, and we use various other things to transform functions into other functions, once we've done the transformation like this, we transform our original functions into new functions like that, and then once they've been transformed into new functions, these new functions can be composed. So by turning, for example, turning the db fetch into bind, we've turned it into a two-track function. By using map on the lowercase in the email, we've turned it into a two-track function, and so on and so forth. And once we've got all these two-track functions, it's really obvious how to glue them together. So again, all these things like monads and stuff is really to make making composition easier. All right, final thing, a web service. So that's one kind of composition. We've talked about two tracks, but another kind of composition, these monadic functions, these like one-track input, two-track output, these happen all the time. And there's another way of composing them other than the two-track model. It's called Kleisli composition. And what happens is you take two of these things and you glue them together and you get another one of the same kind. So this is just like adding two numbers together and getting another number. Adding, concatenating two lists and getting another list. Composing these two kinds of functions and getting another function of the same kind. That's Kleisli composition. Okay? Very important, it's the same kind of thing. This is where this whole concept of monoids comes in. Gluing two things together and getting the same kind of thing back. So there's this library called Suave.io, which is an F# web library, and it has a concept of a web part. And a web part has an input, which is an HTTP context, everything you need to know about the HTTP, the request and the cookies and all that stuff. Okay? And the output is an async of an optional HTTP context. So it's async because it returns not immediately, and it's optional because you might not handle it. You might say, I can't handle this thing, you've given me a get, I can only do posts. So it's got two possible outputs. Okay, so it might fail. Right, so there's a whole bunch of things. Let's look at how this works in practice. So the way you glue these things in Suave is you have this composition, the Kleisli composition symbol, which is an angle equals angle. You glue two of them together and you get another one of the same kind of thing, just like Lego. All right? And because it's another of the same kind of thing, you can repeat. You can add things to that, and then you can take those things and add things to that and make bigger and bigger and bigger things. So here is a web part called path, and it checks the path, and if it works, it succeeds, and if it doesn't, it fails. Okay, so there's success or failure. If it matches or it doesn't match. And then here is a thing called OK. That's a web part, and all it does is set the response, so that always works. Okay. Now, if you take two of those things and you glue them together, you check the path, and if the path matches hello, then you return hello. Okay. So we're just going to glue those two things together, and now we get a new web part. So now we have a web part that matches the path and returns something. Okay. So that's a new web part. And there's another one called choose. And a choose web part takes a bunch of these things, and it picks the first one that works. All right, so all it does is pick the first one that works, and returns it. Okay. So for example, we could say choose between these two things. If the path is hello, return OK hello. If the path is goodbye, return OK goodbye. So if the path is goodbye, the first one's going to fail, and the second one's going to succeed. If the path is hello, the first one's going to succeed. If the path is neither of those, the whole thing's going to fail. So the choose itself is going to fail. It's going to be the bad side of the output. Okay? And then we have a web part called get, which only succeeds if the request is a get request. And then we can take that get and we can connect it to the choose. And now what we have is something that will only succeed if it's a get request and if it's one of those two paths. All right, so now we've built up a more complex thing. And we can build up a complete web app the same way. So we say, if it's a get, choose between these paths. If it's a post, choose between these paths. Okay? And then we just assign that whole thing. We choose between the get and the post, and now we have a complete web app. So this web app is obviously it's a really simple web app. But I mean, it's a web app. There's no objects. It's all functions composed together. And we just say, start the web server with that app, and there you are. So the web parts are connectable and they're reusable, just like the Lego. So it's a really nice way of doing web design because each of these things is testable in isolation. You don't have to set up a whole complicated server to test these things. Each part is individual. There's no strings attached, so each part is testable individually. So this is what a web app looks like. Again, you have your request coming in, you have all these little functions, you choose between which one based on, you don't really have a route or a dispatch, you just have these choose web parts. Okay? No classes, no loops, just pure functions, just composition, just input and output. The power of composition. Right, so let's just look at what we covered. Philosophy of composition, always connectable, no adapters needed, reusable parts. We looked at principles, composable functions, and composable types. Everything's composable. And the final composition, the types of composition, we looked at basic composition, just gluing track together with that. We looked at piping. We looked at partial application. We looked at monads, yuck. We looked at bind, and we looked at Kleisler composition. So that really is everything. If you understand this talk, which you can always go and review it later on the video, but this is really everything you need to know about functional programming right here. If you understand this, you know, there's nothing stopping you going ahead and doing stuff. So thanks very much. This talk will be on my website, F# for Fun and Profits. There'll be slides there. I have other videos there. I have books, including my domain modeling book. And if you want to contact me on Twitter, Scott Wlaschin. So thank you very much.